doing some work story problems. And then we're going to talk about the average value of a function. And both of these are relatively straightforward. There's not a whole lot of new, like, theoretical conceptual stuff, just a little bit of application here. So those of you that are physics knows that force is equal to ma, mass times acceleration. Now, if we think about S as a position function, really Newton's second law would be mass times the second derivative of our position function. Since we know that acceleration is the second derivative of position. And then work is related to force as it's force times distance. Typically, we measure force in newtons, and then work is in Newton meters, which is referred to as a joule. So just a little bit of light physics background. In general, this idea of like work is force times distance and force is mass times acceleration is really what we want kind of moving forward. So let's just kind of dive into some story problems here. So how much work is done lifting a 1.2 kilogram book off the floor to put on a desk that is 0.7 meters high? Use the fact that acceleration due to gravity is 9.8 meters per second squared. Well, we're asking for work, right? Which is force times distance. We know the distance is 0.7. And then the force we'd have to calculate. We know force is mass times acceleration. We're told the mass of the book is 1.2. And our acceleration due to gravity is 9.8. So this is just like a plug the stuff in, like nothing burger of a physics problem, right? Those of you that have taken physics have probably done this a bunch of times, and that should feel pretty comfortable. B then says how much work is done lifting a 20-pound weight 6 feet off the floor. What's the issue here on part B? Yeah, the units, right? We have pounds and feet instead of kilograms and meters. So you can do it one of kind of two ways. You could convert the pounds into kilograms and then the feet into meters, or you could convert your gravity into feet per second. That's probably the route I would go. Physics students, you remember gravity in feet? I think it's 32.
Oh.
Does that sound right?
Sounds right to me.
I think it's 32. So if we just kind of fill this in, so we have 20 pounds and then 6 feet and 32, whatever that comes out to be, like foot-pounds, then is our answer. 3840. Great. Okay. So notice here in both of these problems, the force would be constant because gravity is constant, right? That makes it an easy, like, high school physics problem. But what if the force isn't constant? Now you're talking about, well, then to calculate that work, we'd have to sum the section, like these infinitesimally small sections of force, times that distance that they're traveled. So again, force and then distance, and add up infinitely many of these. What does it sound when we're adding up infinitely many things? Sounds like a integral, right? Like an integral is where you're adding up like a million little tiny slivers or something, right? That's what an integral really is. So let's take an example here. So let's say when a particle is located x feet from the origin, a force of x squared plus 2x pounds acts upon it. How much work is done moving it from x equals 1 to x equals 3? Well, that's my f of x. That's my a and b. So from the formula above, that's all I need to do, right? Oh, Mr. Kulik, how nice. So if you grind that through, let's see, the antiderivatives of those things would be that, and we plug stuff in. And that comes out to be 50/3. And then again, it said this is in feet. Right? Foot or feet, and then pounds. So our answer's in foot pounds. That feel okay? Not a big deal, right? Another common force situation is where you have springs, like you've stretched a spring or you're using a spring. The law governing the behavior of a spring is called Hooke's law. And the force there required to maintain a spring stretched x units beyond its natural length is f of x equals k times x, where k is a constant specific to that spring you're stretching. So any spring has its own separate constant. So let's say that a force of 40 newtons is required to hold a spring that is stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 to 18 centimeters? So we're going to start with our Hooke's law here to figure out K for the spring. So we know the force to stretch the spring is 40. And how far is the spring being stretched? Gosh, that's a tongue twister. 5 centimeters. So I need to write that as a meter though, right? Because it's newtons are in meters. So we got to make sure we do that. So the K here is 800. Everybody feel okay now? So now we want the work done for stretching the spring from 15 to 18. So my force function is K times X. Everybody's okay there? And then what are the bounds? What do the bounds need to be? Not 15 to 18, because its natural length is 10. So 5 to 8. Right? But we need to write it in not centimeters, but meters. They're not going to be insane about units on the AP exam. They're not going to try to trick you with units like they're trying to trick you here in the textbook. It's much nicer than that. It's okay? And then we just grind that thing out, right? I think this thing comes out to be 10,000. I'm going to skip doing the calculus there. Is everybody okay with that? As that's like one of the easiest integrals you'll ever integrate. Okay. Let's go with something that's a bit more challenging here. A 200-pound cable is 100 feet long. It hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? So let's start by writing our force function, right? So what force is acting here? Gravity. Good. And how does gravity work as a force? It's mass times acceleration. What's the mass of our cable? 200. And then, but that's changing, right? As we pull some of this cable up, that mass is going to be decreasing because it's no longer dangling off the edge, right? How much is it when we've pulled 0 up? Let me think here for a second. So how long is it? It's 100 long, right? Let's think about it this way. What I really want, that's a better way of thinking about it. Okay. Let's do that first. So I know that 200 pounds for 100 foot, right? How many pounds per foot? Everybody's okay there? So my force then should be 2 pounds per foot times like my delta x, right? How much cable I've pulled up. Everybody agree with that? And then my distance, total distance I've covered is like x, right? So think about it this way. To pull up like from like 70 feet hanging to 60 feet hanging, what's going to happen there? We pulled up 10 feet of cable, right? Times 2 pounds per foot. So that's my force, right? And I'm sorry, that's my work, right? Force times distance. Why am I not worried about gravity here? Why haven't I like included a gravity? Physics people? What's the unit? Pounds. What's the difference between pounds and kilograms as a unit? Pounds is a weight, kilograms is a mass. Weights are forces, masses are not, right? So that's, they're trying to goober us there. Yes?
Wouldn't it be like, just thinking, like when you start pulling it, you're going to have way more weight to pull than at the beginning, right at the end.
Mm-hmm.
I don't know where. Okay.
Right. The first foot you pull up weighs a lot more than the last foot you pull up.
Right.
100%.
Oh, that's what the integrals do.
Yes. Yes, because if you think about the graph of this, like the graph of 2x, like the area under the curve,
Yeah.
this is like the end of the integral, that, right? Or like the start where you have to do a ton of work versus the end where it's almost no work.
Right.
Right? Does that feel okay?
Yeah.
So, yep, you're on it. Katie? I was just doing a hypothetical. I was just doing a hypothetical to try to show, like, why what I'm integrating is 2x dx. Yes, 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 yes. All right. One more example here. I know you guys love these. A tank has the shape of an inverted circular cone with a height of 10 meters and a base radius of 4 meters. Is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all of the water to the top of the tank. The density of water is 1,000 kilograms per meter. So let's think about the picture here, what we got going on. So we have an inverted circular cone. We're told that it is 10 meters high. The base has a radius of 4 meters. And we're filled with water to a height of 8 meters. Everybody's okay with that? Okay. So now what we're asking to do is to pump this water like up out of the tank, right? So how far does that initial first circle of water have to get pumped? 2 meters. By the time we get to the bottom, how far does that have to be pumped? 10 meters. So what's changing? The height that we're pumping. What else is going to be changing though? The radius of the circle of water that we're going to be pumping, right? Because we're always going to be pumping from the top down. And as we start, we have a big circle of water that we're pumping. By the time we get to the bottom, we have a little tiny circle of water that we're pumping, right? So what I want to do is I want to take this and resolve it into a single variable. So I know this is 4, and that's 10. And then I'm going to have some radius, I'll call that like Ri. That's like the radius of the circle of water, or maybe let's do Rw, maybe that's maybe more obvious what I mean. And then this height of the water how can I represent that? I'm going to call this distance like x sub p, like the distance we have to pump the water. So the height of the water then is just 10 minus that distance we have to pump, right? Because that height of the water is going to be changing each time as well. Everybody agree? So notice what I've done is I've gone ahead and described those two heights using the one variable. Everybody's okay? That'll be necessary on something like this because you can't have height to pump and then height of the water separate as two separate variables. You have to reconcile that into a single variable. And then furthermore, we can write this as a proportion. So we can say like 4 over 10 equals Rw over 10 minus xp. So I can say that Rw equals 40 minus 4xp over 10. So far, so good. Okay. So remember, I need a force, which is mass times acceleration, right? And then I need the distance to be pumped. Well, I know what that is. That's just xp, right? But I need to get a force out of this. So I know that mass, well, the piece we haven't used yet is this density piece, right? So what am I going to do with that? I'm going to use that to get the mass, right? So I know that like mass is equal to volume times density. So my mass of water that I'm going to be pumping is, well, my volume. And the volume for this is going to be, it's going to be pi Rw squared times the height of the water, right? Now I'm going to substitute in for what Rw is. So far, so good. And just for cleanup's sake, I'm going to take that 4/10 squared out. So I can just have 10 minus xp cubed. I haven't put it in yet. Oh. Sorry. Yep. Yep. Still need the like times 1,000 at the end here. Oh my goodness, guys. So hold on one second here. My apologies. So I've made a mistake here. The mistake has to do with this. Because how much water am I pumping in an instant? Not the entire tank, right? What am I? How much am I pumping? Like a tiny little sliver, a dx. Very good. Yeah. So that should be like my delta x or dx. Using either there would be okay. My apologies. Fix that in a second. And notice that this is going to be in what unit? Kilograms, which is a mass as opposed to a weight. So to turn this into a force then, I need mass times gravity. I'm going to reduce 4/10 to be 2/5. Is everybody okay with me doing that real quick? It just feels less annoying that way. Oops, and I still have that 1,000 in there somewhere, right? Okay. So far, so good. Now my work is going to be the integral from what's the initial pumping distance going to be? 2, right? And what's the final pumping distance going to be? 10. So that's my integral. This goes from 2 to 10 of this force oops.
Can it just be dx at the end?
Yeah, I mean, I'm going to move that. I'm going to put it here, and then I have times that distance, right? XP. So this is all the force. And this is like the distance. And then it's just calculator time.
Is this considered a relatively challenging?
Yes. Yes. And to be in all honesty, when you do stuff like this on the AP exam, it won't be this physics-centric. It'll be more like an accumulation problem, like something is happening at this rate, how many things happen over this time interval. And it's just like, oh, I just integrate the rate function. And it's usually pretty straightforward. Again, I think these tend to be more challenging than what you'll see on the AP exam. And I ask you to just try a handful of these. Okay. Questions so far on this? Again, it's just one of these that you have to kind of get your hands dirty and you get the hang of them. There's not like a lot of theory going on in the back. Well, there's theory, but it's physics theory, which I'm not qualified to instruct you guys on. The other idea that I want to talk about is the average value of a function. So we know how to calculate the average value of a list of finitely many numbers, right? You just add them all up and divide by the quantity of numbers you've added. But how do we calculate the average of something that's infinitely many, right? Like if I talk about, well, what's the average temperature that day? How many temperature readings could you have taken during the day? Infinitely many, right? Like what the heck does average temperature mean? But we use it, and trust me, they're doing it. So let's talk about like what that would mean. So let's say y equals f of x is a continuous function like our temperature function. And we're worrying about that defined on the interval from a to b. So like a is this morning and b is, like 12 a.m. and then 11:59 p.m. or something, right? Like the day. So we'd start by dividing the interval into n equal length subintervals. So we're going to split that interval from a to b up into n equal size chunks. And then we'll call the length of each of these subintervals delta x. And we'll choose a sample point from each subinterval and evaluate each of the sample points with our function and then average those values. What are we starting to sound like? This is an integral, right? This is the exact same thing that we described when we started defining what an integral means. So we take all of our sample points and divide them by n. And since delta x is b minus a over n, we know that n is b minus a over delta x. And if we do a little bit of clever rearranging, we get this. And if we just assume those subintervals to be infinitely small, i.e. taking the limit as n goes to infinity, we have an integral. So if we're looking for the average value of the function on the interval from a to b, it's 1 over b minus a times the integral from a to b of f of x dx. Now, common misconception, average rate of change, slope, instantaneous rate of change, derivative, average value for a function, integral. So we hear average and sometimes conflate the two. I just want to make sure that we're clear as to like the vocabulary there. So if we think about this graphically for some positive function, say we have like, this is a and this is b. Actually, let's make this a and this b. We have that area of that thing divided by the width would equal like some average height. Actually, let me draw a better picture than this. Okay. Let's do something like that and make that A and that B. So like that's the area under our curve, right? If I take that area and divide it by the width, I'd get like a height for a rectangle with the same area as my integral. Everybody agree? And that height is really the average value for our function. So notice along the way, is there a place where f of x takes the average value of the on the interval from a to b? Yes. So let's do some numeric examples now, right? The idea here is fairly straightforward, even if the idea is kind of fuzzy, like the execution of the idea is very straightforward. So it says find the average value of the function f of x on the interval from -1 to 2. So that's it, right? That's our setup. Everybody feel good there? So 1/3, and my antiderivative would be x plus x cubed over 3. So I plug things in. I have 2 plus 2 cubed over 3 minus -1 minus -1 cubed over 3. So far, so good. So let's see, what do we got here? We have 1/3, and then we have 2 plus 8/3 plus 1 plus 1/3. That's going to be 6 times 1/3, so 2. So the next question that usually gets paired with this, particularly in the AP sense, is, okay, is there some value, is there some C on the interval from -1 to 2 such that f of C equals that f average? Okay. Find it. So what do? We just, oops. We have 1 plus x squared equals 2, right? So I subtract 1 from both sides. We get x equals plus or minus 1. So there were 2 values, in fact, here where on the interval. I guess if it was an open interval, same question, right? And then you have just one answer then, but okay. So again, think back to our temperature example from before. Is there some time C such that the actual temperature equals the average temperature? So again, we're looking at, is there an f of C that's equal to f av? Or other words, is there some C where the integral of f of x is equal to the area of the rectangle whose height is f of C and whose width is the interval that you're integrating over? And the answer to this is always yes, is provided that your f of x is continuous. So again, if we think back to the example I drew before, here's another picture. No matter how you draw that, if it's continuous, you got to be able to find that C on there. Everybody's cool with that idea? If you think about it, if I take this and fill it in there, that should fill up that area, and it kind of eyeballing it, it looks like it would. All right. So let's do another couple of examples, and I think we're done here. Since f of x is equal to x plus 2 is continuous on the interval, the mean value theorem says that there is a number C inside the integral, or I'm sorry, inside the interval, such that this is true. Right? So we're saying that 2 is equal to 1 plus c squared. Oops, that's not 2 anymore though. That's a, you boo-booed that, Mr. Kulik. That was 6. Times 3. And we get the same thing, right? C is plus or minus 1. We did it before. It's the same idea. It's the same thing that we did right here. It's the same work, it just rearranged. Do whichever way it feels easier to you. I always think about it this way because it's just like just a solving problem. That's what I prefer to think about it as. One more example. Show the average velocity of a car over the interval from t1 to t2 is the same as the average velocities during the trip, or the average of the velocities during the trip. Do you get what I'm saying? So let's say that s of t is our position function. And we'll say like v of t is our velocity function. So the average velocity would just be the slope, right? So it's how much distance we traveled divided by the time it took to get there. Everybody's okay with that idea? Now, the average of our velocities is our average value integral. So far, so good. What's the integral of velocity? Position. And if I do my definite integral, that's going to be s of t2 minus s of t1. And if we put that all together, we see that, hey, that's the exact same thing we had before. And we're done, right? Does that feel okay there? I mean, the hardest part was like getting it started where it's like, okay, I need to define a position function and a velocity function. Like, this is really all it's asking us to do. And again, I ask you to do a handful of these. Again, fairly straightforward, right? They're just asking you to calculate the average value. They give you a function. They give you an interval, like relatively easy calculation. Or they give you the function, then they ask you to find the average value, find the c, and sketch the rectangle. If you didn't want to sketch the rectangle, I wouldn't be mad about it. Does this feel okay? I'm going to stop here because this was 2 things to do, and that's enough, right? For your virtual day, I have 2 things on the MyAP for you to work on. So one is a related rates practice question. Another is an optimization practice. I picked these specifically because I know you don't feel good about them. These are like the two things from first semester I feel like everybody feels the worst about. And we're just going to start like trying to trickle in some more practice. We have one more section of content and exam, and that's it. One more test. So again, looking through the content library on what I am still going to do, we're going to talk about integration by parts. And then we're going to do some differential equation stuff. And that's it. That'll be test 3. So we have these two ideas, like these integral story problems where we're doing some kind of accumulation story problem. The book specifies these all as work problems, but they could be like anything, right? The integral of a rate gives you a total. And then I might do a little bit of like select stuff maybe from one or two of these if we have a lot of time left. But after that next test, we're just going to be trying to prep for the AP exam. So I'd like to have this next test wrapped like end of March, beginning of April. And have the rest of April to just, I know there's a spring break in there for 10 days that we lose, but that probably gives us 2 weeks or so to kind of just do some practice for the AP exam. So we'll do some practice tests. We'll do some of those in class where you can get a feel for like what that's going to feel like. And then we'll do some targeted review of stuff that like we feel bad about. And it's like, okay, can we go back and reteach any of these things or do a little bit more exampling? But that's the plan for the rest of the semester. So I have like one more test. And I think I'm going to, in lieu of homework quizzes for this next test, because we've already kind of gotten away from them, I'm just going to be dropping in some more like first semester review stuff in place, so that we're kind of coming back and circling back and working on those things. It won't be high stakes. You'll have a partner, you know. They're just quiz grades. It's only 10%. We've already got a bunch of them booked. We drop a couple at the end. It's no big deal. But that's my plan for the end of the semester here. So I want to, you know, that last month or so, I'd like to be relatively low stress, at least for this class, where we've got all the content wrapped up and we're just kind of in the process of reviewing. Sound okay to you guys? Because I've moved fast through some stuff here, and you guys have been really good sports and have worked really hard and put us in a good position to where it's not like we're going to be scrambling to finish content by the end of the year. It'll be, you know, just doing some things that I think are interesting or good things for you to see in combination with some review. So anything probably past that test that I do content-wise would be just like, here's, you know, like half a class of me talking, and here's a handful of problems to work on. And that'd be it. I could give you some take-home stuff to do review-wise, which I think is good. But that's my plan. You know, if we have a lot of time, maybe we'll take all 4 sections in class timed and just let you feel how that feels like beforehand. I think is often going to be beneficial. You know, since you got to do it at some point anyways, right? But I'd like to do, once we've wrapped, do some timed practice, and have stuff that we can like score out, and you can kind of see how many marks you're going to get from what you did or whatever. I think is helpful, especially the multiple choice stuff where it's really like, you know, you got to be careful on how long you're spending on some of these multiple choice questions, especially if you have no calculator. Like some of those, you can really go down a rabbit hole. It'll give us opportunities to talk about like maybe what was the quick way of doing this? What other way could you think about this? What did Mr. Kulik see when he saw this question that he was able to do in 10 seconds? Because those are good. Like that's important. Like practical test taking help. That's, you know, that I want to be able to have time to provide. Elena. Go ahead. I'm already off topic.
Could we do number 4 from 6.4 instead of first book?
Oh, sure.
I started looking at it.
6.4, number 4. Let me drop that in. Okay. So when a particle is located a distance of x meters from the origin, a force of cosine pi x over 3 newtons acts on it. How much work is done moving the particle from 1 to 2? Interpret your answer by considering the work done from 1.1 to 1.5 and then from 1.5 to 2. Okay. So I know that my work function is just this, right? That's my formula for work. So our force function, we're told, is cosine pi x over 3. If I do this on my calculator, we could do that. Do you want to do it by hand?
Would I have my calculator question like this one?
Probably, but this is one that's eminently doable by hand. It's like a little teeny U-subber. Okay. When you get this, I think you get 0. Would be my suspicion looking at the problem. I'm going to put a question mark above that. And it says, okay, interpret your answer by considering the work done from 1 to 1.5. And then the work done from 1.5 to 2. And I'm guessing that like this is going to be like positive A and this one would be like negative A. And that's how you end up with 0.
Oh, is that it?
That's all it's trying to get you to look at.
So that's the whole problem?
Yeah.
Oh, it's so much simpler than I
Yeah,
thought.
let's grind this out real quick and double check and make sure that what I suspected was happening is actually what's happening. Hi, geese. And good, I am in radian mode. Yeah, so I basically 0, right? If I go from there to there, I get some positive number. And then if I go from 1.5 to 2, I get the negative version of it. So yeah, it worked exactly like I thought it was going to. That feel okay, Elena? And for the most part, like, that's how easy these problems are. Like, you might catch 1 or 2 that are more like the rope or the volume thing, but like for the most part, they're just like, here's your force function, here's your distance. Like, do your integral. Wait, Jacob, sorry.
So the one we were doing is like an example. It's like right above this one.
Uh-huh.
How is it only 3 joules? Oh, it's
3.4
10
times 10 to the 6th. Yeah. Yeah, it's like a million joules.
When I plugged it in, I got like 8 million. Maybe I plugged it.
Yeah, I don't know.
Because X, like when we plug it in, the XP you just use X, right?
Correct. Yeah.
And then the XP at the end, you could just put next to like the 1000, right? And obviously just put the X at the end.
Mm-hmm. Yeah, that should be right.
I don't know what I did. I copied it.
What mode is your calculator in?
Gradient.
Okay. I always ask because I don't know the mechanics of how they're doing these approximations, and it's very likely they're using
Right.
some kind of weird power series or something to do these approximations. I haven't dug into the code enough to look at how it's actually doing it.
Alright, I got it. Forgot to square the 2 bits.
Ah, yeah, that would do it, right? You had me curious now.
It should work.
Yeah. Yep. That'll do.
I just forgot.
Happens to the best of us.